So back home I have my white apple core, and I was thinking about materials, and sometimes I've had a couple decide not to work because the wire gets stretched, breaks on the inside, even though the rubber on the outside of my wire doesn't break. So anyway, it's probably not because of it being wound too tight, we'll see. So here's the side view of my apple core, and I'm wrapping it around the inside. That's right here. And this is a side view of my wire. You have the rubber, which has a thickness of 0.004 inches. That's not actual specs, but anyway. The diameter of my actual metal wire here, I'm just going to assume it's a solid metal in here. That's what we're trying to solve for. What is the minimum diameter for that metal so that it does not break, given a certain normal strain allowance? This is the cross-sectional area of my apple core right here. And I'm wrapping my wire around it. Okay. And if I zoomed up on a little pie section of that, I have my thin rubber, I have my metal wire, and I have another thin rubber, and the rest of this is my apple core in here. In order to solve these kind of problems, we have to first start with where is the neutral axis, which is right through the center of our wire. Let's just label some of these distances here so we can reference them later. So this is the diameter of the wire. This is the thickness of the rubber. And we said that was 0.004 inches. I estimated the radius of the inside of this apple core to be a ½ inch. The total radius from the center of our circle to our neutral axis is, we're just going to call that R. Our big radius here has to be from the center of our object to our neutral axis. And that's always the case. It's the center of our rotation, or center of our circle, our curvature, to our neutral axis, wherever our neutral axis is, which is in the center of whatever object we're considering, which is the wire. This next picture, it kind of explains how we are deriving our formula for strain. So this is just our wire. This is just the metal of our wire. This is our neutral axis right down the middle, and this is the outermost fiber, or the outermost part of the metal. It's going to be slightly longer. If I bend something, this will be slightly shorter, compressed, and this will be slightly longer in tension. And so we only want it to have this amount of strain. This is our allowable strain. So what is strain? Strain is just displacement divided by the length, our elongation divided by total initial length. So how much longer did it get? Well, L2 minus L1. And how long was it originally before it was bent around our apple core? It's just L1. So this is just a small chunk. So this being our small chunk, we have L1 at radius R and angle theta. It doesn't particularly matter what our theta is, because we'll see it's going to cancel out later. This is just a derivation. So L1 is just going to be the arc length of that circle. So that's just R times theta. L2 is also an arc length, but it's slightly longer, and it's slightly further out from our center. We have to add half of the diameter. Here we have to add the radius of the wire to get from the neutral axis to the very outer part of the wire. Radius plus half the diameter gives us our full distance from the center to where we're talking about, times our theta gives us our total length for L2. Okay, so let's plug these in up here. These are our same formulas as before. I put my R theta wherever I see an L1, and I put the L2 expression wherever I see L2, which gives me this. Now I distribute this theta, and I notice that my R thetas cancel. So that leaves me with dw theta over 2r theta. Then my thetas cancel out. And I'm left with strain equals the diameter of my wire divided by 2 times the radius. My radius, however, also has an expression That was the radius of my apple core plus the thickness of the rubber plus the radius of my wire. So that's the expression for that. I have this formula, but the objective was to find the minimum diameter of the wire. So I need to solve for my diameter here. First I'll distribute my 2 across. Now I can multiply the denominator over to the other side. So at this point we have strain, we multiply times, this is the radius of our apple core, plus 2 times this is the thickness of the rubber around the wire, plus the diameter of the wire itself, equals the diameter again. So I'm going to distribute my strain through. Now I can isolate my dW's by putting dW epsilon on the other side. And I factored out my dW here. I can isolate dW by dividing by 1 over epsilon here. I have dW by itself, and this is my expression. Now, do we have a number for our strain? We do. We were given an allowable strain rate. We were given the radius of the apple core. We were given the thickness of the rubber. So we have everything we need. Let's plug it in. Those are the numbers that we get. And in the calculator that comes out to be 0.137 inches, which is possibly a little big for the diameter of a wire, but that's fine. It works out. And that's it.